In this lecture of electrical measurements, I'll be discussing about characteristic of measurements. So what is characteristic? Characteristics describe the performance of an instrument. It allows the user to select the most suitable instrument for specific measuring jobs. There are two basic performance characteristics of measuring instruments. They are static characteristic and dynamic characteristic. Now the static characteristic, the value of measured variable changes slowly, and also it describes the performance of instrument related to steady state variables only. So that is what the static characteristic. Whereas the dynamic characteristic, the value of measured variable changes vastly with respect to time. Now coming to the details of the static characteristic, as I already told you, it changes very slowly with respect to time or remain constant. Now coming to the different static characteristics of electrical measuring instruments. First one is the span and range, where range is the highest measurement possible and span is the difference between maximum and minimum measurement possible. For example, take the case of voltmeter and having a specification of 0 to 300 volt. That means here the range is 300 volt and span of the meter, a voltmeter, is 300 minus 0, that is 300 volt. Another example is for the purpose of temperature measurement, we are having range of the instrument ranges from minus 10 degrees Celsius to 150 degrees Celsius. So that indicates the range, and the span will be a difference between that two. So it will be giving 150 minus of 10, so it is equal to 160 degrees Celsius. So in this way we will be defining range and span of the instrument. Next one is the mean, spread and standard deviation, where mean, as all of you know, it is the average of the values of the same measurement taken, and the mathematical expression is given by, if you want to take the average of values of x, which is differentiating moving from 1 to n, then the mean is given by x1 plus x2 etc. up to xn divided by total number of measurements taken. Similarly, the spread is deviation from the mean. So the mathematical equation is given as, it is the mean of the or the calculation we want to know, and each instant what is the value minus the mean, that will provide the spread. So that will give an information about deviation, how much it is deviated from the mean. Next one is the standard deviation. Standard deviation is given by the relation square root of the values taken from 1 to n divided by total number of measurements taken minus 1. So that will give the standard deviation. So these all are all measures we will be using for the purpose of statistical analysis. So next one is the accuracy and precision, where accuracy, it is the closeness with which an instrument reading approaches the true value of the quantity to be measured, and precision is the degree to which repeated measurements show the same results. For example, we can able to take here you can able to see 3 circles, and the first circle we will consider, and here this is the actual value of the system, that is the yellow circle is the actual value to be measured, and these are the precise values. So this is the true value and these are the precise value. So from the first figure it is clear that the precise values are not near the true value. So this system is not accurate. And also if we are seeing the precision of the same, we can able to see that the precise values also, they are not very near. If they are near, then only it is repeated in the same. So it is not precise also. Now we will take the case of the second. Here you can able to see that the precise values, that is the measured values, are away from the true value. So it is not accurate. But if you see the measured values, they are very near, they are almost reproducing the same impact, so it is precise. The second one is not accurate, but it is highly precise. And the third one is, you can able to see that the measured values are very near to true value, and also the measured values itself, then they are very near. So in the third case, it is accurate as well as it is precise. So next static property is resolution and sensitivity. Where the resolution, it is the smallest detectable incremental change of the input parameter that can be detected in a output signal. So for the smallest change, it can able to make an output corresponding to the input. Then that we call it as, that system we call it as, it is precise. So that can be measured by means of the unit scale, multi-range meters, etc. Next one is the sensitivity. Sensitivity for an instrument or sensor with the input x and output by, sensitivity is equal to dy by dx. That is the small change in the output that is to the small change in the input, that gives the sensitivity. For example, if the measured output is increased from 100 millivolt for a temperature change of 40 degrees Celsius, then sensitivity is given by the difference between the output, that is 100 millivolt, divided by the input change, that is 40 degrees Celsius. So it will be providing 25 volts per degree Celsius. So here it is expressed graphically. Here is the sensitivity graph, the slope of the calibration curve. The output is the signal output. The y-axis having the signal output, and x-axis which is having the variation of the physical variable. So here the most sensitive is the set point. That is the most sensitive because this much variation from the input output, a high variation you can able to see as compared to other two cases. It is only this much variations. So next one is the dead zone or dead space and dead time. The dead zone or dead space is the largest of a measured variable for which the instrument does not respond. For example, here you can able to see the graphs that the output is given in the y-axis and the input which is given the x-axis. Even though this much input from 0 to this point, the input changes, there is no change in the output. So that space we call it as the dead space or the dead zone. And the next one is the dead time. The time before the instrument responds after the measured quantity has been changed. That is, till this one it won't respond. So that time we call it as the dead time. After that the changes occurs. For example, camera and data acquisition card, there you can able to see that even though you are providing an input, it will take some time to respond to the input provided. So this can happen only because of the friction in mechanical measurement system. Next one is the linearity. Sixth static characteristic is the linearity. Here, if input-output relationship is a straight line passing through the origin, then we call that system as linear. For example, linear voltage differential transformer. So that is what the full form of LVDT, which is a linear one. So in LVDT you can able to see that, we will study later detail into LVDT. So in that one you can able to see that as the displacement changes over the positive and negative directions, there you can able to see a change in difference in the voltage, and that also it's linearly varying. It crosses the zero and it's linearly varying. And another one is thermistor, which is a transducer. Here as the temperature changes, the resistance value will changes, and also you can able to see that the curve is not linear. So next one is the next static characteristic is tolerance. Maximum deviation of the manufactured component from some specified value, that we call it as the tolerance. When we buy something from the market, some equipment or something from the market, then we will be getting a data sheet. In that one, clearly if you check, then clearly they will be mentioning the tolerance level. For example, take the cases of the resistance value of a resistor. It is expressed as 10 or plus or minus 5%. So this 5% we call it as the tolerance. So it indicates that this resistance can vary from 10 minus 5% of the ton or 10 plus 5% of the ton. That is, it can vary, real value can be between 9.5 ohm and 10.5 ohm. So that is the tolerance level. So the next one is the static error or absolute error, where static error is the average value of the same measurement. So that is expressed as epsilon 0 on delta I, that is equal to the measured value minus true value. So a measure of measured value minus true value, we call it as the static error. Relative or fractional error is, which is a unitless quantity, that is expressed as epsilon r is equal to the static error divided by the true value of the measurement. And the final one is the percentage error. Percentage error is equal to epsilon r into 100, that will give the percentage error. So these all are the static performance indices of the measurement system. Next one is the dynamic characteristics. The performance criteria for the measurement of quantities that changes with respect to time. That is what the dynamic characteristics are. There are mainly three dynamic characteristics. The first one is the speed of response. This is defined as the rapidity with which an instrument responds to the changes in the measured quantity. So how much speedily an instrument which is changing with respect to its input, that measure we call it as the speed of response. It will provide a measure of active and fastness of the system. Second one is the fidelity. It is defined as the degree to which a measurement system is capable of faithfully reproducing the changes in input without any dynamic error. So once we will making a measurement under certain condition, and if we are repeating the same measurement and same set of conditions, then the output should be the same. A measure of that one we call it as the fidelity. And the third one is the lag. Lag is the every system requires its own time to respond to the changes in the input. So this we call it as the lag. We have got two types of lag. One is the retardation lag, another one is the time lag. The retardation lag, as soon as there is change in the measured quantities, the measurement system begins to respond. Then we call that system having a retardation lag. And the time delay means the response of the measurement system starts after a dead time. Once the input is applied, they cause dynamic error. Actually, the response of the measurement system after dead time, if it is starting, I already explained what is dead time. So if the system having a dead time, then automatically that goes for the dynamic error of the system. And the dynamic error means it is the difference between the true value of the quantity that is to be measured, changing with respect to time, and the measured value, if no static error is assumed. Without assuming a static error, if there is a change in the high change in the measured value and the true value with respect to time change, then we call it as if the system has got dynamic error. So these are the dynamic characteristic of measurement system. So in this session we have discussed characteristic of electrical measuring instruments. Thank you.